Welcome everybody to PALS, February 10th, 2026. Today's speaker is Claudia Muresan, who will be speaking about abstracting congruence extensions through complete joint semilattice morphisms between commutator lattices. Claudia, please.
Thank you. So I hope my laptop doesn't get lazy again. So some of you may have seen part of this talk at the MAS meeting last year. So it's a little longer now, but honestly, the final part I'm in the process of curating. It's based on two papers, one of which is under revision at the moment. All right, so here's what I'm going to talk about. The original case is that of algebra extensions. Actually, if you're familiar with the paper by Dr. G. and McGovern and a few other authors about extensions of commutative rings, those are the extensions we will be generalizing in this case. So first of all, we've generalized them in a previous paper to algebra extensions. So if we have two algebras from the same variety, so two algebras of the same similarity type, we had the case of algebra extensions, and instead of talking about ideals in an extension of rings, we were talking about congruences of these algebras. Sorry that my writing on the screen is as it is. What I'll be talking about now is the abstract case. So what we had for congruence extensions, so we had the canonical inclusion morphism between the algebras A and B, and we were interested in its action on congruences. So we had a morphism that we denoted like this, which simply took congruences of A to the congruence of B generated by this congruence of A. And this is how we studied extensions of algebras, and those, well, the basic property would be a listing property, right, for ideals. So we would have the same thing for congruences. And we are looking now at an abstraction for this case of algebra extensions. So instead of the lattices of congruences, instead of these lattices, what we have are two commutator lattices, because you may know that congruence lattices are commutator lattices when endowed with a term condition commutator, provided this commutator is distributive with respect to arbitrary joins and, of course, commutative. This commutator is important because in order to study these extensions, we need to investigate algebraically and topologically the primes with respect to this commutator. So instead of taking mid primes elements in the lattices of congruences, we take prime congruences with respect to the commutator. All right, so instead of congruence lattices, we are going to have arbitrary commutator lattices. Now, we are interested in some abstraction for this map, which in this case, I repeat that it takes congruences of A to the congruences of B generated by these congruences of A. Well, it turns out it's easier to, or at least more practical, because we have not found an abstraction that can actually particularize or concretize if you want. I don't know if I'm using my English right. So which in the concrete case can actually be proven to be a canonical embedding between two algebras of the same similarity type. So what we're going to be looking at is actually the general case of maps in the variety V between two algebras. And then instead of that map corresponding to the canonical embedding, we are going to have a map like this, which takes congruences of A to the congruence of B generated by f of alpha, for alpha congruence of A. Of course, by f, I mean here f times f. So morphism from A times A to B times B, which I'm restricting to congruences of A. So I'll be restricting it to the set of congruences of A. And then its image is going to be formed of congruences of f of A, of the algebra given by its image. Okay. And I hope I'm not mistaken. Yeah. So if we take the congruences of B generated by this f times f, so let's say f squared of these congruences of A, then that is the morphism we'll be interested in. It turns out to be, well, unfortunately, not a lattice morphism, not even, so it does preserve the join. Actually, it preserves arbitrary joins. It doesn't necessarily preserve the commutator. It doesn't necessarily preserve the intersection of congruences. So this morphism, this F bullet, is going to be, in the abstract case, a map between these commutator lattices, which preserves arbitrary joins. Okay, so we are going to be interested in such morphism, and of course in certain properties of the lattices L and M and of their commutators to describe this abstract case for algebra extensions and more generally for maps between similar algebras. So of course we can look at the particular case of algebra extensions. So then how would these congruences behave? So basically, so we're also going to be interested, apart from this map, we're going to be interested in its inverse image. So we're going to have a map F star, which is going to be the inverse image of this F times F. We're going to restrict one to the congruences of B. So it's going to be defined on the congruences of B. And then its image is going to be in the congruences of A. Okay. Now, if F is a canonical embedding, so if A is a subalgebra of B, then who is going to be IAB star? So this inverse image applied to a congruence of B. Okay, I'm gonna refrain from writing this, sorry. So with beta of congruence of B. Well, it's going to be exactly its restriction to A. So I'm going to write here beta intersected with the one class congruence of A. So this is just A squared. Okay, so this is the behavior of this map on congruences. In the case of congruence extensions, we're going to be interested in the general case of morphisms between two similar algebras. And who is going to be F star if instead of H, we take the map, which I've denoted F bullet, which takes congruences of A to the congruences of B that their image through F generates. Well, it turns out that this map is going to be precisely a map I'm going to denote like this. I mean, we denote it in our work, okay? Which is exactly its right adjoint. So the map which forms with H a Galois connection here. So H preserves arbitrary joins. H star is going to preserve arbitrary meets, and is going to have the usual properties. And we'll see why we are interested specifically in this map. Well, it's probably already kind of obvious that we need to look at something like this to study extensions of algebras and more generally maps between similar algebras from the point of view of their action on congruences. So again, I apologize, I have to write here on a fairly small screen and my writing is horrible like that. Okay, so I'm not going to refer to the this definition of the term condition commutator. Just note that it is a binary operation on the lattice of congruences of a member of a variety of algebras of the same similarity type. And also here I have a problem with the full screen. What I can do is this. It's most unfortunately that I cannot hide this bar. Can I hide it? I think I'm gonna give up on the full screen in my external viewing app. Okay, so I'm sorry that it's the view is going to be a bit smaller. All right, so the important thing about this binary operation on a lattice of congruences, at least for a start, is the fact that it is smaller than its arguments, so than their intersection, and it's order preserving in each argument. And for congruence modular varieties, don't worry about its particular definition in this case either. So for congruence modular varieties, it is also commutative and distributive with respect to arbitrary joins. So this is the kind of commutator that we need for our constructions and to study algebra extensions and more generally morphisms between two algebras from the same variety from the point of view of its action, so the action of such a morphism on congruences. So I will get back to this particular case a bit later. Let's also note a property of the commutator in congruence modular varieties, so property of the modular commutator. It has this property on quotients. Now I've decided not to refer to this property in the results from this talk, but maybe it's nice to see it though. So obviously we can write it on quotients because if you have two isomorphic algebras from the same variety. Then if you take the term condition commutator, then the commutator lattices of the congruences of these algebras will be isomorphic as commutator lattices. So you're going to have a lattice isomorphism, which also preserves the commutator between them. So this property of the modular commutator is equivalent to its case on quotients, which looks like this. So this quotient, so congruence of A, is precisely the commutator. So the definition of the commutator in the quotient algebra. Okay, this looks spectacularly ugly. So I'm gonna write it again here, although it's probably not going to look any better. So who is this quotient congruence? Well, it's exactly the commutator in the quotient algebra of these congruences of the quotient algebra. Okay, so I don't know if that is more readable than what I had written before or not. So what you can see here is that the canonical projection map, so the canonical surjection map, and obviously this means that in general surjective maps in F have this property. So again here what I write by F is F times F. So this square of F, which is defined between these product algebras and restricts to congruences. This I'm usually denoting simply by F. And this is what I'm talking about here. So this is precisely F bullet in the particular case of this map. So let's say P theta bullet applied to alpha beta. Provided that the commutator of alpha and beta includes theta. And here again, we would have P theta bullet of alpha, P theta bullet of beta. Okay, so I didn't get back to these notions, so you probably can't follow them right now because I'm going to get back to the definitions. I'm just referring to the property of preservation of the commutator. I think it's written here as condition 3. This second part of the third condition. Here it is. So this preservation of the commutator is going to be satisfied in a very particular case. But in many more cases, we are going to have a sort of sub-preservation of the commutator. So we are going to have this inequality. I repeat that the map H that that appears in these conditions is in the particular case of maps between similar algebras. This would be the map F bullet, which takes congruences of the first algebra, two congruences of the second algebra generated by their image through F. Again, by F here, I mean F times F. Okay. So my point is that preservation of the commutator by this map is a very restrictive property. So this map, and obviously to properly find an abstract case for this, these notions, our arbitrary map between two arbitrary commutator lattices, we won't be able to ask of it to preserve the commutator or the meet in these lattices, because this map doesn't always preserve the intersection of congruences. Or we're going to be able to ask of it is that it preserves arbitrary joins. So let me get back to the definitions. So this would be the case of algebra extensions and maps between similar algebras. Okay, one more observation. In congruence distributive varieties, so varieties in which all members have the lattices of congruence is distributive, the commutator equals the intersection. So we have this property. And in this case, congruence lattices are frames. So when the commutator equals the intersection, then this congruence lattice is a frame. So it's not only a bounded distributive lattice, and of course it's algebraic because it's a lattice of congruences, but it also has the meet completely distributive with respect to the join. So the intersection is going to be distributive with respect to arbitrary joins. All right, so let's move to the abstract case. So a commutator lattice is complete lattice, considered as a bounded lattice. So we take its lattice bound, which is endowed with a binary operation called commutator, which is commutative, smaller than its argument, and completely distributive with respect to the join. Of course, since it's distributive with respect to the join, and of course in both arguments because it's commutative, it's going to be order preserving in both arguments. And when the commutator is the intersection, is the meet, then this bounded lattice is a frame. And of course, frames are exactly the complete lattices, which can be endowed with a commutator operation equal to their meet. That would make them commutator lattices. So the notion of commutator lattice is an abstraction for the notion of a congruence lattice endowed with a commutator, which behaves like the modular commutator in the sense that it is commutative and distributive with respect to arbitrary joins, besides being like all term condition commutators, smaller than its arguments and order preserving in each argument. Okay. So it's this case that we are interested in. So the case in which the commutator is commutative and distributive with respect to arbitrary joins. But of course, we are not interested, for instance, in the modularity of the lattice L that you would have in for congruence lattices in congruence modular varieties. So we just want the commutator to have these properties. Okay. So for instance, you can have an algebra whose commutator, whose term condition commutator is commutative and distributive with respect to arbitrary joins. But that algebra doesn't have to have congruence modular. It doesn't have to have a modular lattice of congruences. And even if it does not need to generate a congruence modular variety for our results to hold. Okay, so just a note that this is what I'm going to use as a notation for commutator lattices. So unless I'm mentioning otherwise, the components of the bounded lattice will have the usual notations. And I'm only going to specify the notation for the commutator. So for instance, a congruence lattice, I'm going to denote like this with its term condition commutator as a commutator lattice. And of course, such congruence lattice, if its commutator is commutative and distributive with respect to arbitrary joins, will be an algebraic commutator lattice. So you probably know that algebraic means compactly generated. So each of its elements is a join of compact elements. Consider the prime spectrum with respect to the commutator. So the elements different from 1, which are prime with respect to the commutator instead of being mid-prime. So this is the prime spectrum we are interested in. I'm denoted it like this for arbitrary commutator lattices, and for the case of congruence algebras with term condition commutators, which behave like the modular commutator in terms of commutativity and complete distributivity with respect to the join. This will be the notation for the prime spectrum of congruences of such algebras. And out of these prime elements, I'm also interested in the minimal primes. So the minimal elements of the prime spectrum, which I denote like this. And for algebras, for congruence lattices, I denote like this. Now, what we can notice about the prime spectrum is that if the commutator of 1 with itself is 1, then it includes the coatoms of the lattice, which, so the set of coatoms is non-empty, so there exists at least one. If the lattice is non-singleton and its top element is compact. I'm not gonna use this, but well, I mentioned it anyway. This would be its notation for lattices of congruences. Now, regarding these conditions, so what do they represent for congruence lattices? Well, for instance, the top elements of congruence lattices are always compact in semi-degenerate varieties, so varieties with the property that no non-singleton member of them has a singleton subalgebra. So for instance, any bounded structure, if you take bounded lattices, for example, if you have a bounded sublattice of a bounded lattice, then if the big lattice has 0 different from 1, so if it's non-singleton, then so it's its bounded sublattice. Okay, so for instance, the variety of bounded lattices is semi-degenerate, and obviously any variety of bounded lattice ordered algebras will be semi-degenerate. The same for the variety of rings with unity, again semi-degenerate. All right, so this bar is pretty stressful. I can't get it out of the way, sorry. Right. Now, in congruence modular semi-degenerate varieties, we also have this condition, and more generally, so not only the commutator of the top congruence with itself, not only this one equals the top congruence, the one-class congruence, but moreover, The one-class congruence is a neutral element with respect to the commutator in each member of such a variety. Okay, so here are the topologies we are going to use. First of all, the stone topology, which is also called spectral topology, okay, on the prime spectrum, which is formed of these open sets for each element of the commutator lattice. So for each element x of the commutator lattice, the open corresponding to x is the set of the primes which is not above x. So the closed sets of this topology are these sets. For x in the lattice, its associated closed set is the set of the primes above x. Okay? And if the lattice L is algebraic, so if it's compactly generated, then if we take these opens for the compact elements of L, we get a basis for the stone topology. And this topology obviously induces the stone topology on the minimal primes, whose opens are for each L, for each x in the lattice L. The open corresponding to x is formed of the minimal primes not above x. These will be the closed sets of the stone topology on the minimal primes. And obviously this bar is getting most uncomfortable. Okay, I think it's better like this, although the view is getting smaller and smaller. All right, and if the lattice L is algebraic, then again, if we take the opens for the compact elements, we get a basis for the stone topology. This is how I'm going to denote the prime spectrum endowed with the stone topology. This is how I'm going to denote the minimal prime spectrum endowed with the stone topology. And we also need the flat topology, also called inverse topology. We have such a topology on all the primes when the lattice is compact. Otherwise, we don't have a corresponding of this topology on all primes. But we do have one on the minimal primes. This is how I'm going to denote it. You've noticed the notation for the stone topology. So the one on all primes and the one on the minimal primes, okay, with a calligraphic S from stone. And this is going to be denoted with a calligraphic F from flat, okay? So on the minimal primes, it's by definition the topology generated by the closed sets corresponding to the opens from the basis of the stone topology on the minimal primes. Okay, so we take for each x compact, we take this set, which is the set of the minimal primes above x, and we take all of these sets, and then we consider the topology that this set of sets generates. And this is the flat or the inverse topology on the minimal primes. And this will be actually a basis for this topology. And this is how I'm going to denote the minimal primes endowed with a flat topology. So it's also called inverse topology, and this is the classical notation for it. Okay. So I repeat that we have something like this. So obviously we're going to have to exclude this intersection. We have something like this on all the primes if the lattice is compact. Otherwise, we don't. All right. And this is how I'm going to denote the stone topology on the minimal prime congruences for an algebra A. And this is going to be the topological space corresponding one. This is going to be the flat topology on the minimal prime congruences. This is the corresponding topological space. The stone topology on all prime congruences and the corresponding topological space. And in the case when the congruence lattice is compact, then we're also going to have a flat topology on all the primes, and this will be the corresponding topological space. Okay, so let's finally move to our main result. We are going to need some more notations and some conditions. I'm not going to use the implication. I'm only going to use the polar in what follows. So the polar of an element of a commutator lattice will be denoted like this, and it will be the top element of the annihilator of that element with respect to the commutator. Okay, this is the polar, and I'm also going to be interested in this congruence of a commutator lattice. So this will be a congruence lattice, a lattice congruence, which also preserves the commutator. And moreover, it preserves arbitrary joins and collapses the commutator with the intersection, meaning that the quotient through this congruence will be a frame. So consequently, it's going to be organizable as a commutator lattice. I don't know why my laptop won't let me. So as a commutator lattice, this is going to have the commutator equal to its meet. Okay, so who is this congruence that I'm gonna use? Well, two elements of L are congruent if and only if they have the same primes above them. So this is equivalent to the radicals being equal. So the radical of an element is the intersection of the primes above it. So it's the intersection of the primes, which are bigger than X. So they're in the principal filter generated by X. So two elements are congruent if and only if they have the same radical. Okay. So you may notice that the radical of 0 is the intersection of all the primes. And this is important for algebras. Sorry. For long talks. For my breathing, I need to take a mint in the middle of the talk. Sorry about that. So for algebras, condition that the radical of the bottom congruence, so the equality, is equal to the equality. So the condition in the abstract case, the condition that the radical of 0 is 0. So this condition means that the algebra is what's called a semi-prime algebra. And for instance, in semi-degenerate congruence modular varieties or algebras, all algebras are semi-prime, if I'm not mistaken. Anyway, in congruence distributive varieties or algebras are semi-prime. Okay, so
Claudia,
okay.
let me just mention something that the seminar is going for another 10 minutes or so. So I see you have like 2/3 of your slides are left, and you may want to focus on like the main points.
Okay. I just saw that.
Is that possible?
No, sorry about that. Okay. So let's I'm gonna try to wrap it up. Sorry, I thought I have more time. Okay, so this quotient. So let's look at this frame. We have this subset of it. This subset of this quotient frame. In the particular case of congruence lattices, this is precisely the reticulation of the algebra when these conditions are satisfied. So what does it mean that it's reticulation? It means that it's a bounded distributive lattice, a sublattice of this, such that its prime spectrum of congruences, of course, with the stone topology is homeomorphic to the prime spectrum of this lattice of ideals of this lattice. So the prime spectrum of its lattice of ideals endowed with the stone topology. Of course, this is a frame. So as a commutator lattice, it has the commutator equal to the intersection. So I'm actually referring to prime ideals here. So the usual prime ideals, because the commutator equals the intersection. Okay, so under these conditions, this is what happens. Okay. So, I'm going to try to wrap it up. All right. I'm going to refer to the condition that the only element which has no primes above it is 1. This happens if 1 is compact and equals its commutator to itself. Okay. And slides are stuck again. Heaven's sake. Come on. There we go. Okay, so I'm going to need these conditions. So if you take a look here, this is part of the condition for so algebraicity is obviously satisfied by congruence lattices. And then we have these conditions, which in the abstract case are the fact that the set of the compacts is closed with respect to the commutator. And the only element which has no primes above it is 1. So this is the condition in which we have the reticulation for an arbitrary algebra. I'm going to call it the condition on compacts. And I also need this condition on prime ideals, which says that any minimal prime of this quotient lattice, so of this quotient through this congruence, any such minimal prime generates a minimal prime ideal in this lattice, okay? So you may notice that when the lattice is compact and it satisfies this condition, in particular when the lattice is compact and the commutator of 1 with itself is 1, then this lattice satisfies the condition on compacts. And when the lattice is compact, it also satisfies the condition on minimal prime ideals. Now, you remember the condition for semi-prime algebras. It's the condition that the radical of 0 is 0. Okay, so let's finally move to studying such morphisms between two commutator lattices, which preserve arbitrary joins. As I mentioned before, such morphisms such maps have a unique right adjoint. So they form a Galois connection. No, sorry about this. Trying to hurry. I'm doing a terrible job out of it. So they form a Galois connection with a map, which is defined like this. So for any B, this is the value of the right adjoint of H, which we denote H star in B. So the unique map which satisfies this condition. And I repeat that for a morphism in V, we have this map which acts on congruences like this, whose right adjoint is precisely this inverse image of S times F restricted to congruences. Okay. Now, what we may notice about this map is that it preserves compact elements, preserves arbitrary joins, of course, it satisfies this, so it actually preserves principal congruences moreover than its preservation of congruences. We don't have a good description for principal elements in the abstract case, which is why I'm not going to refer to them. We are going to refer to compact elements and a distinguished set of compact elements. And let me see if I can show you something meaningful from our results on extensions. All right, so our map F bullet, so the one which corresponds to the map H in the concrete case, satisfies this sub-preservation of the commutator in congruence modular varieties. In a very particular case, it actually preserves the commutator. Okay. Now this condition, sub-preservation of the commutator, and actually also preservation of the commutator, it's satisfied for the elements of a subset of the lattice, if and only if it's satisfied for any subset of the lattice, so the elements of any subset of the lattice in which this subset is joint dense. So what I'm saying is that if lattice is algebraic, it suffices to enforce this condition for compact elements. Okay. And okay, this is very important results, which is a characterization for primes, for minimal primes among primes, which is what we use in many of the following results. We do use the reticulation in some of them. Now, regarding the lattice structures of these topologies, the stone topology on primes is a bounded sublattice close with respect to arbitrary unions of the Boolean algebra of the power set of the primes. The same for the stone topology on minimal primes. Now, this one for all the primes is isomorphic to this frame, but this one is also a frame, so they are both frames in terms of the lattice structures. Now, the one on minimal elements is a Boolean algebra. It's actually equal to the power set if the lattice is finite, and moreover, if there are finitely many minimal primes. While the flat topology is equal to the same power set of the minimal primes, again, when the lattice is finite, but moreover, when there are finitely many minimal primes and all their intersections are compact. Okay. So in general, when the radical of 0 is 0, and one of the two conditions on compacts and or on minimal prime ideals is satisfied by L, the flat topology is coarser than the stone topology. And if the set of compacts is close with respect to the polar, in particular if the lattice is compact, then the two topologies coincide. Regarding reticulation, so this lattice, when the condition of compacts is satisfied, the stone topology on all primes is homeomorphic to the stone topology on the ideals of this corresponding lattice of the reticulation, this abstract version of the reticulation. And the same goes for the stone topology on minimal primes and the flat topology on minimal primes. Now, under the same condition on compacts, the flat topology is compact and T1, so almost separable, okay? So meaning that if you have two distinct points, then you have a separation like this with an open surrounding one of the points, okay? Okay, when do the two topologies coincide? Well, under the condition on compacts and the radical of 0 being 0, precisely when the stone topology is compact, case in which it's also T1, and don't worry about this condition. Okay. Now, if all primes are minimal primes, then the stone topology is compact. And if the radical of 0 is 0, we also need a condition that one is compact here. If the radical of 0 is 0, the compacts are close with respect to the polar, and one of these conditions is satisfied, then this is Hausdorff, so not only T1, but actually T2, and consists solely of clopens. So this stone topology on the minimal primes is a complete Boolean sublattice of the power set of the minimal primes. And just trying to wrap it up. So yeah, we have some nice results on extensions. So on these maps between commutator lattices. So these complete joint preserving maps between two commutator lattices. So in very remarkable cases, the right joints are continuous with respect to the corresponding topologies and even homeomorphic with respect to those topologies. So I'm just going to show these results very fast. So under some natural conditions, L and M being algebraic, so compactly generated, the top element of one being compact, H preserving compacts as it's corresponding in the concrete case does, H sub-preserving the commutator, and this condition is what's called mean admissibility. So the right adjoint of H taking minimal primes to minimal primes. Then this right adjoint is continuous with respect to the stone topologies on the minimal primes and the flat topologies. Under remarkable cases, it's continuous from the stone to the flat topology and vice versa. Again, no, sorry about this. Okay. If it's injective on minimal primes, then with some extra conditions, we obtained that it's a homeomorphism between the stone topologies and between the flat topologies, and from stone to flat, and from flat to stone. And I'm not going to present the next results because they are not exactly curated. They're from the submitted paper. So we have abstractions for results of Bhattacharjee G and McGovern on extensions of commutative rings. So it turns out that you can treat quite a lot in this abstract case from those ring extensions. So the abstract case of the behavior of on congruences of morphisms between algebras of the same similarity type. I repeat that we treat this in the abstract case through joint preserving morphism between two commutator lattices. And yeah, sorry I didn't have time to insist on these. Maybe more on our main results, basically. So at least if I explain the basics, maybe if you see my talk, you can easily follow our main results on homeomorphism between these topologies. Okay, that's about it.
Thank you. I have a question. So you have these hypotheses off to the side, CP and ID. Can you remind me what CP and ID stand for?
Mm-hmm. Okay, so condition CP is what you would ask of an algebra, in the concrete case, what you would ask of an algebra for it to have a reticulation. So remember that we have this congruence, and the quotient lattice through this congruence is a frame. And the abstract version of the reticulation would be the set of compact elements, its quotient with respect to this congruence. So when this set of compacts, when it's closed with respect to the commutator, this is a sublattice of this one. So it's going to be a distributive lattice. 0 is compact, so it's a sublattice with 0. And if 1 is compact, then it's a bounded sublattice of this frame. Okay. So when 1 is compact and the set of compacts is closed with respect to the commutator, this is a bounded sublattice of this frame. So this is a bounded distributive lattice, and it has the properties of the reticulation. So it has this this homeomorphism property, and moreover, we find homeomorphism for the minimal primes endowed with the stone topologies and the flat topologies. So this is the condition on compacts, which is an abstract version of the condition you would enforce on congruences of an algebra for that algebra to have a reticulation. So for it to have such a bounded distributive lattice, whose prime spectrum of ideals endowed with the stone topology is homeomorphic with the prime spectrum of congruences of that algebra with its stone topology.
And the ID is?
Yes.
What is the ID?
And the one on ideals is this one, that in this quotient lattice, so in this quotient lattice, the minimal prime elements generate minimal prime ideals. So obviously the prime elements do generate prime ideals. The trouble is that if these elements are minimal primes, so if these are minimal among the primes, then these ideals might have prime ideals below them, which obviously will not be principal. So they will have to be infinitely generated prime ideals. But they can have prime ideals below them. And we do have an example of such an algebra which does not satisfy this condition. So which has a minimal prime such that the prime ideal it generates is not minimal prime in this lattice. It's not a minimal prime ideal, okay? So it has a prime ideal below it. Okay. Of course, it can be principal, okay? But it exists.
All right, thanks. Does anybody else have a question?